Swayam Prabha. Digital India. Educated India.
Yeah, we still have the definitions, but we lost the meaning for that. Okay, so this model was created somehow backwards from a final model. So a lot of things are there which shouldn't be there yet because we are not there yet. Okay, so at the moment it contains two so-called portions which you can find here on the right side. On the right side, there are here two tab pages. One is called custom portions, other is called auto portion. Portions are maybe a bit strange name in Consteel for group of elements. You can use a portion for many reasons. You can even put them, assign them in portions that you say already checked by my friend, or I'm not sure if it's good enough, or to be replaced tomorrow, or to be shipped to the job site, already produced but not erected yet. So you can do what you want. And in addition to such categorization, you can assign to these portions also mechanical or Consteel controlling meanings as well. So the way how to create a portion, you can create as many portions as you want. You need to give a name, and you can assign in under this portion any sort of elements, and then these can be called together. In order to define this boundary between a column and beam, which is the zone for connection problem, and therefore as an exclusion zone for the beam-based design, we need to say which are the elements which we believe are to be considered here. And the way we tell to Consteel is through the definition of a custom portion. Because here we already have some, anyway we can use it. I don't know if you have these, probably you have them, okay? So the left corner name at the moment is visibly, it's empty. So if you activate it, you see nothing on the screen. That means that it's empty at the moment. Now, in order to not keep it empty anymore, let's select the first one for the left side, the column, and the lower rafter.
So from what you did before, you've already created that custom portion?
No, it's actually you made it, and I just deleted it to give them a starting empty model, but I forgot about the fact that you had these already. So that's why they are. They shouldn't be there, but they are there.
Ordinarily, you would create that custom portion, and now you're going to put things into it.
Yeah. So normally you don't see, so it's not that every Consteel model has these then by default. Only this has because he made it. Okay, I was just not careful enough to delete. Okay, now let's take benefit that it's already there. So we select the elements what we want to assign into this one. It's a bit strange logic how you do. You need to select the name. So not this something in front, but you need to click on its name of the portion. And then there is this modify icon there. You click on the icon, and there are three options. Add the selected elements to portion. This is what we need. You can also remove the selected element from the portion, and you can also say that you want only these in the portion and none of the others which might be already there from a previous operation. Okay, so we need the first step. We say OK. When you click OK, then they come here. To check if they are really there, you need to activate it. Activation is by clicking on this box, not clicking on the name. So this is a bit strange. And now we see that really only these two are there. There is also a nice functionality that we can see in a bit, okay, not now because I selected such a color that doesn't make the rest visible. Okay, so I will not do. But by this you can see in a hidden way all the rest of the structure, and only those elements are strongly visible which are in that model portion where we are. If you don't want this model portion or any of the model portions to be active for display, then you can switch them off, and then we see again the whole structure. Let's put also the elements into the right corner. Again, select the column, select the lower rafter, click on the name of the corner, modify, and the first one, OK. If we activate the portions, then if you select the top one, then it will automatically activate all the portions which are listed. And then this way we can see what are the elements which are in any of the portions which exist. Okay, so this is fine. And now we can come to this frame corner wizard. And what we can do now is we just say that egészségedre, that would be Hungarian. So you select these two elements and you select the very first at the moment. If you do, this is something that works in a very complicated way. Then if you don't see, if it happens, you are supposed to see a box which represents the corner zone. Now, if you don't see it, there are several reasons. You made something wrong, or just the visualization is switched off. If the visualization is switched off, then you will never see, even if you did it well. It's definitely switched off. So if you come here to the visualization, we already saw during the last 2 days that for many reasons, if you don't see something or you don't want to see, you can come here, and for each type of object, you can switch off the representation from the screen. This seems to be a nice thing up to the moment when you switch off also those things which are relevant, but you forget that you switch them off. And then you suddenly don't understand your model anymore because it seems that you have no more supports. You start to define the new support set, and then you will have suddenly 2 supports at the same position. And when you start the calculation, Consteel will say, no, you have too many supports. And you say, oh. Okay, so be careful with this game. If you click on the frame corner, then suddenly these boxes will appear. So with the way we did with this frame corner wizard, both need to be selected with the shift, the name. Select first this ugly, unspecified type of connection, and click apply. When you do so, they will have this gray color. As you see, this box might be also yellow later on, or green or red. But the default, the very first option is to be gray, and now they are gray indeed. And this, as we expect, it means that within this region, Consteel will not make any more beam-like design. Don't forget the connection design must be done. Consteel has at the moment a built-in module for connection design based on Eurocode. Nothing based on AISC and nothing based on Indian standard if you have anything specific for connection design. So at the moment we don't have that. So when Consteel is just, in that case, would start to check the columns from column base up to this point, and then from this point to the top of the rafter, then the design is not complete. So connection design is still missing. That must be performed somehow. And unfortunately here, Consteel cannot help yet. If it was a Eurocode project, then yes. If it's an AISC or Indian standard project, then no. Okay? But now we speak about stability of members. So now, once we did so, let's try to give another try. Let's run the calculation again, this time with these boxes already implemented, and go back to global check. I go back again to the first buckling mode, which we know that it's not good, but let's see that maybe the situation is already a bit better because we are not checking anymore those cross sections which are in a region where we are not supposed to check. Now, from the second result, we see that that region became black. Black means no utilization. It doesn't mean that it's good or bad. It just simply means that it was not calculated. We know why, because we told Consteel, please don't calculate it. So it doesn't mean that it's okay, the structure. It must be covered by a connection design problem. But as purely from a beam approach, that is not covered, not to be calculated, therefore we don't say that it's red anymore. Okay, but we still see some problems here below. If we come to the 102%, now if we check that connection, calculate connection, we see that it is still using the 2.94, which is probably, or we clearly saw that that value is still the one which refers to the rafter and not to the column, so it probably makes no sense to use this value for the column. Now here comes a very interesting in-house developed feature of Consteel, which can be activated on the same analysis screen by selecting the very first not selected option, what we call here as buckling sensitivity. This, when you activate, when you run the calculation, then by first it seems that nothing happens. You get exactly the same type of results. But if you just blindly repeat the calculation for the global check, suddenly a third option becomes available, which says automatic assignment of the buckling modes to the members. So not only the first is available, which would give, without thinking, the first to each of them, or not the second, which means that you as an engineer, you said that use the second or the fifth or I don't know one, which to all of the members, but you can select automatic. Automatic means that from this buckling sensitivity analysis, it gives an advice, it gives an automatic assignment of the a link between members and the buckling mode shapes. And based on this, the members will not be calculated for the very first anymore, but if you select this option, then you accept to use this automatic assignment from Consteel. And if you run the calculation again, then again we cannot see huge impact on the results because not LTB is the governing at the moment. But if we call again to this cross-section, what we wanted, then we will see that now, nicely, without saying anything, not the very first mode was used for the column, but something else. Let's see what was the 3.88. 3.88 is definitely the second buckling mode, which is to the column. Okay? So the first is still to the rafter, without saying anything, without me selecting this mode and saying, forcing the calculation to be performed for this mode, also the column. Consteel was automatically using this mode for the column. And now, for example, if we select this less exposed cross-section here, then we can see that for here, a buckling mode with 7.62 was chosen. This is certainly not the first and not even the second. We haven't even seen which one is that, but we can see which one is the 7.62. No, it's probably was not even the second. Yeah, that was load combination 3. So here, not even load combination 2 is relevant, but load combination 3. So with load combination 3, 7.62, this is the fourth. Okay, and visibly, clearly, nicely, that is really something to do with this part of the rafter and not with my column. So what this method is doing is assigning the different eigenvalues to members. Now, how is it done? It could be done. For this, there is no any code regulation or sophisticated calculation. This is a in-house developed, I believe, relatively smart approach, which considers every buckling mode as a possible deformation. All these, the eigenvalues they are not millimeters, they are just numbers. You can convert them into imperfection by multiplying it with the scaling factor to change them into millimeter, but they are just numbers. But doesn't matter that they are just numbers. You can say that let's multiply them with 1 millimeter, and now they are already deformations. They are continuous deformations around the structure. They fulfill all the compatibility requirements, as we saw on the first day when we thought about this continuity by adjacent members. The rotation of the connected elements is something that makes sense, so they rotate together based on the stiffness, based on the stress level, elastic stress level. So they are a deformation which are realistic deformations, so why not calculate deformation energy from them? It's just simply stiffness matrix multiplication. Anyway, we already have the stiffness matrix for a section. We just multiply the stiffness matrix with the deformation, and we calculate deformation energy. Deformation energy is strength multiplied by displacement on the second, and multiplied by 0.5. So 1.2, 1/2 times stiffness multiplied by displacement. This the same type of energy that we have, movement energy, spring energy, and any type of energy is calculated this way. So what we do is that we have this sort of deformation as a this buckling mode, we multiply it by 1 millimeter, we change them into a deformation, and we, for each of the finite elements, we calculate the associated deformation energy. And then what we do is that we don't know exactly how many joules or some, I don't know what is energy, what? I don't know. But it doesn't matter how much is that, because again, we don't know the scaling, but it doesn't matter. That's not relevant how much is really the physical value. What is important, what is the distribution of this energy over the structure? Because we say that at those parts of the structure where there is visibly a high concentration of this energy, those are the points which are probably the relevant parts, and those where this energy from this given mode is very little, those are the parts which are probably not relevant. We just scan through the whole structure for each finite element, we calculate the deformation energy. We find the very big, the biggest number, which can be, doesn't matter how much. We say that this, we scale this value up to 100%. This will be the maximum. All the others are proportionally scaled with the same ratio as the given number up to the 100%. And as such, we get a map of this percentage around the structure. This map can be shown by finite element displacement, and also we can say that we integrate all these values along the members, and we show the values not by finite elements but by members. So to accumulate all these energies member by member, and then we show them not by finite element but by member distribution. And then the 100% will be the maximum value, and proportionally all the others the lower value. So for example, what we can see that from this mode where visibly the biggest deformation was here, if we take also into account the section there, and which is stiffness, and we calculate deformation energies, from this concept is also visible that these are the most exposed locations. Here, this result is, there should be something with 100%. Now here, it's 100%. Doesn't matter how much it was. We say that the maximum is 100%, and then proportionally we show all the others. And what you can see also numerically here, what we could also expect from just by visualization, this impact disappears very quickly. So we have 100% here, 80%, quite big numbers, 20%. Again, surprisingly, in the contraflexure part, there is again a relative increase up to 92%, 60%, 7 in the adjacent member already 17, 1, 9, 2, 3, 0, 0, 1, 1, 1. In the columns, nothing, 0. In the rafter, 0, 5. In the column, nothing. So this is a sort of numerical explanation also to that visual feeling that this buckling mode has a certain high relevance for that part which is located here and not elsewhere. And that's the logic what is used by this buckling sensitivity analysis. If I activate, for each of the buckling modes which were calculated, we perform the creation of this map for the distribution of the deformation energies, and we assign a given buckling mode to the member which produces the maximum, obviously the 100%, so that's no hesitation, that will be assigned. And in addition, we assign any other members which are producing relatively high accumulated value. We could even say that we just assign the one which has the 100%, but that would be probably a very unsafe situation. To be definitely on the safe side, we have defined a range. Higher the range, more safe the calculation is. This assignment is an automated process. It helps the engineer to have a good advice on the buckling mode to use. You may always override this assignment if you want, but based on our experience, this works extremely well, especially considering the fact that these buckling modes typically have a very local relevance anyway. So it doesn't really matter how much we put this scale factor, this effect disappears very quickly. At the moment, the lower value, what we have set in Consteel, is 10%. So that means that we will assign the element with the 100% and all the other elements which are producing at least 10% from this mode. So in that case, it may mean that we add also another element, but certainly, definitely not the one, not the column, for example, which is 0. Okay, so it's really it works very nicely for those which are definitely separated modes. So it's very nicely separating the well-separated modes. And if a buckling mode seems to be relevant not only for the one where the maximum value is given, but also to the neighbors, as a safe side decision, we also assign this mode also to the neighbors. It might not be the most relevant, but there is a certain chance. And to be always on the safe side, we do the assignment. Okay? There is also a graphical representation of this. There are two graphical representations of this. One is that this sort of map, as I said, the upper value, this MRF, it means mode relevance factor. So this will be always 100 for the most relevant member, and the number is calculated for each of the members. Here you can see this is the accumulated value. Here you can see on this rafter that while this is 100%, this one is only 0.3. This is 0.18. Column is absolutely 0. The column on the other side is also 0, and this one is 24%. 24% is not 0. Based on our judgment, as this is more than 10, there is a certain danger that this could be affected. Probably it makes sense that if this part was selected, visibly the waves are continuing also into this member. So it would be very strong to say that, yes, it definitely is valid for this one, but it's definitely not valid for this one. To be on the safe side, as the 24% is more than 10%, we say that even this mode will be accepted to this buckling mode. Okay? If we go to the very first mode, which is valid for this rafter, as we saw already, is clearly to this part of the rafter, where visibly also there are the biggest waves, but it has almost 100, it's 83% mode relevance factor on the lower rafter, so obviously this will be also assigned. If we come to the column, it's still 0. If we come to the opposite group, the 0.68, 0, 0. Okay? So finally, what happens is that we can create such a map where we can see an envelope of all the assignments. I just selected now to see absolutely clear picture. I have now rerun the calculation only for the second, no, to the third combination, which we know that it's one of the relevant, second or the third, the relevant. And now if we come back to the analysis, buckling sensitivity, to this summary of the results, then we see this distribution. And here, all the results are referring to the combination number 3. And now the question is that from the combination number 3, to which member we assign the first mode, to which member we assign the second mode, and to which member we assign the third or any further modes. Here, by colors, everything is visible. Unfortunately, we don't show the number of the mode, only the multiply, but that can be easily back-checked. So here it is seen that for the column 388, rafter 2.2, rafter 2.2, other rafter 7.62, 4.87, 4.19. So 1, 2, 3, 4, 5 different values were assigned fully automatically. Now, if we check what these values correspond to, then again come back to analysis, buckling, we are mode 3, and the 2.2 is this. 4.24 was not used because it is still relevant for the same member, but this member has already received a lower value. So once a member gets a number, we will not assign any higher value to that member anymore, because that would represent a higher critical load that would be certainly unsafe. We need to stay with the lowest critical load, with the longest effective length. Okay, so this will not be used. Wait, I check back again, because maybe it's even better to make I can also put a marker on these, and then we can better check how good this assignment was, at least by inspection. Okay, so now the 2.2 was found for this part, for the whole rafter, which based on this, it's something which makes sense. The next mode is...
And everything is with load combination 3 here?
No, this not, no, sorry. No. I should have also made the, no, that is still a mix. Now I calculate only load combination 3 to make sure that that is clearly, yes, and I need to make for this. Okay, so this is my map. I come back to analysis, buckling, load combination 3.
So generally your map
so
has different values at different points that correspond
yes,
to
that's a bit misleading.
Right?
That gives some sort of, if it's run for one combination only, then it works well. Then it really gives that from that given combination, which mode was assigned to which members. Once you run it for more combination, what it shows starts to be a mess. It gives you a certain feeling that at least you have, at the end of the day, no member which has got nothing. But it's not very relevant. So if you are really willing to go into this, it's always better to just select that very one combination what is relevant and just limit this game for that. Now here the results are more understandable. So they all refer to load combination 3, and from which might not be the relevant combination for every member.
Design, right.
But if we just limit our game now to the load combination 3, then for the rafter, the whole rafter, regardless of the fact that I made it from 2 members, 2.2 was recommended, which is this mode. The next mode, 4.24, this would be relevant also to this part. We didn't assign to any of the members because this would be relevant to the rafter, but the rafter has got already a lower value, therefore we skip this. We go to the next one, 6.30 is still on the rafter is fine, we skip this. Next one is 7.62. 7.62 is assigned to the rafter on the other side, so it's fine. 7.93 is assigned to the column. 8.81 is again rafter, we skip. 10.89 other rafter, we skip. 11 rafter, we skip. 14 the rafter, we skip. And now probably it seems that none of the calculated are fine. Therefore, this remains green, and R means not relevant. Not relevant means that none from the calculated mode was giving anything serious and visibly impactful on this column. Now, there might be two things. Don't forget, I said that I'm interested in combinations up to 20. And I calculated, based on this criteria, 16 buckling modes. So none of the 16 was significant enough for this column. Now I can have two choices. I can start to increase my limit to calculate more, accept more, and try to see when do I get to that one which will be fine. Or I use my engineering judgment and I say that even if I don't see it, that will be more than 20. If it was less than 20, it would be here. I asked 20 to be calculated, I got only 16. So that means that this is at least 20. The impact, if you would calculate with the load multiplier or critical load multiplier of 20, any sort of slenderness, that would be so little that virtually it has no any meaning from global buckling point of view. Actually, that's the reason why Eurocode suggests to look only to the up to 20 with the load multiplier. So you can force to have it calculated if you want, but probably it's just waste of time, but as a learning curve, it makes sense. But practically, it means that there is no importance of that, even if it's calculated. Anyway, you as an engineer can always say that for some elements you don't perform a buckling verification because by feel you say it's not relevant. It's basically it's our decision. We typically try to calculate the critical members. Which one is critical? It's based on experience, feeling of the person. So here there is a certain indication that from load combination point 3 point of view, it doesn't mean that this is not relevant for any of the combination. Load combination 3 is not relevant. If we go back to this map, so if I activate again all the combinations, so not just the third, but each four, sorry, and I come back and make the verification again. I don't even need to make the design, it's not there. For buckling, I look to the map, this is still irrelevant. Now I already see the envelope of all the modes, and this is still not relevant. Why is not relevant? Don't forget, we have loads only from left to right. Wind is a very dominant action on the structure, and if there is any wind, that will probably reduce very significantly the force. We can even see how are the internal forces on this column. Most probably there are very little, everything is, if we go back to the envelope, let's see, for example, for the normal forces, 164. Now, from this point of view, is no big difference. But if we look to the, there's not so much, but this is 500 and this is 440. So definitely they are lower. They are less exposed to this column. So based on this calculation, those 16 modes which were calculated, which are fulfilling this requirement that have a load multiplier less than 20, none of them was found, assuming that the wind is always blowing from left to right. Of course, if I was adding the other type of wind direction, then I would see the load combinations which correspond to those which produce the relevant effects on the right side column. The mirrored load cases would give now the same results to this column. Okay, so this is buckling sensitivity. So if you activate it, then and you run the calculation, then you have here for the analysis result an extra result type where you can see all these maps and all these assignments. And in addition, if you go to global check, this option for automatic becomes active and you can select it. You don't have to, but of course if you don't want to select it, then it's better not even waste time by performing that calculation for. So the calculation itself, what is done, is not a standardized method, is not written in the Eurocode or AISC or elsewhere. This is based on a rational engineering idea. We made also papers for that, but actually the idea is not even coming from us. It comes from a Ukrainian mathematician called, I don't know, something like Perelmuter. He was the one who has recommended this first for a bit slightly different application. And we just implemented in Consteel, okay? There is another thing, if we already started to speak about the corner, because we were already there, that, as I said at the beginning, unfortunately, we have no any B moments, we have nothing, because we haven't applied loads out of plane. But if you look to these buckling modes, then you can already see that these are, even if I haven't applied any load in the out-of-plane direction, the buckling modes are always appearing in the direction where the structure is the weakest, which is almost always out of plane or torsional type. So if you look to these buckling modes, then we can recognize that there are heavy torsional displacements and everything like that here in the structure. So here comes obviously the question that a line element is nicely, the flanges are waving and everything is nice. Most of the column is doing nice, but what the hell happens here in the corners? How Consteel will be able to fit together these, the continuity of the flanges or all the other thing? And in general, what we can create so many different types of configurations for the corner and do all behave the same or not, because we didn't say anything to consider how is actually the connection looks like. We always say that please don't consider this at all, but that's not too much information about how it really looks like. So I just made unfortunately this is in the latest version of Consteel. Consteel, the newer versions are able to open the old files, but the old version is not able to open the new files. So by mistake, I saved this file in Consteel 18, and since that, I'm not able to open it anymore in Consteel 18. But anyway, you will have the chance to see it. Actually, if you are interested, you can all download this official version, so your student or trial license fully entitles you to download this one. This is the Eurocode version of the software.
If you're designing Eurocode,
yeah, you
you're,
can design
you're
by
good to go.
Eurocode.
Right.
Don't be misled. This official version also has an option called AISC, but that's not this AISC. That's a traditional type of AISC where you need to specify somehow buckling length yourself. And it works in a very competent way, so don't even try it, okay? So now this looks a bit different. Again, if you feel that you would love to work with Consteel, you can already, we will have a Consteel user seminar in May, where we also accept models from students from everywhere of the world, so maybe you already start to, you will not be able to stop after this seminar working with Consteel, and you will create something. You are free to send in your models. Doesn't matter what you create. We are happy to see anything and everything. Okay, now I already have here a model called frame corners in this newer version. And here for this starting, there will be more. So first of all, I just made such a small corner where there are two ordinary beams coming into each other as they are, without saying anything about what they are and how they are. We can do some calculations for them. And when we do the calculation for them, based on the, basically we consider warping, if no other information is available, we consider this warping transfer absolute analogically to any other type of internal force transfer. So exactly the same way as we transfer a bending moment, we can mathematically do the same also with the warping. It's also very important for the bending moment. It typically, all the finite element calculations are assuming that this Bernoulli-Navier hypothesis is valid, that the cross sections which are connected are rotating together. But imagine we have a very deep eye section, just a shallow eye section, and you don't put any stiffener into the other element, and you apply a bending moment to this one. What is the chance that they will nicely rotate together? They will not. So when in a traditional software we do what we always do, we somehow always assume that there will be a smart engineer who will put there a connection which will somehow make the work. That you will put some triangular stiffeners maybe to somehow make the transition of the deep and shallow elements a more continuous something. So that's a connection problem. It typically doesn't appear in the frame analysis software with sub 2000 or ETAP, so it doesn't matter which one, you just put the deep and the shallow and you run the calculation, and that will assume that the stiffnesses are nicely equilibrating each other. But if it's really happening or not, well, it depends on the connection. But without thinking too much, we can also transfer the bi-moments like this. Mathematically it's possible, although in case of the bi-moment, this is probably even more important to know how the real connection really looks like, because everything depends on that. But we can do something without saying what is it. Now I made, in Consteel, you can work not only with beam elements, but you can also work with shell elements. So I started to make some models with shell elements. No, I don't. Yes, I made models with shell elements as well. So I made the same type of models, so a column and the beam connected together, but I used a bit more of information about, sorry, this is not visible very well. Yeah, here is better visible. I used for the first one this sort of box configuration, but is very often used for meta buildings, that the flanges are continued into the adjacent element, and finally the web panel will be framed by flanges and stiffeners. Of course, some of these plates are stiffeners welded into the one element, others are end plates or the flange of the element. So it doesn't matter, but they are all framed together. Another typical solution is if we cut in 45-degree elements and then we connect around them. Usually it's used for a bolted connection. It's practical from bolting point of view because the lever arm of the bolts are higher. So that's also possible. And there is also another solution, which is basically the mix of the two. Framing plus also, just to be sure, also this is place. Of course, this is more labor cost in the job site, not in the factory to produce. And I'm not very sure that engineers are really aware that what if it has any impact. I think very often people believe that they put this diagonal only to prevent the buckling of the shear panel and not assigning any other meaning to that. But actually it's very interesting that this is not only about that. I applied on each of them a torque, so a pair of horizontal forces on the beam, and with the shell elements I made a calculation to see how they behave. And actually it's very interesting. So the same rotation is applied on the beam, and then see what happens with the columns, with how the column is free to rotate at the bottom. If I apply the rotation on the beam is in the same direction. In one of the cases in the box, the column rotates into this direction. In the other case, the column rotates just in the opposite direction. And in the third, it doesn't rotate at all. And this is something very interesting because normally I think no one would expect that this happened, and you don't even see it, and probably you don't even know about this. That's clearly coming from the fact that how the warping deformations, which are just flange bendings, not necessarily the same. So the flanges may bend in the opposite direction. That's called warping. And really just the question, how that information from here, how we let go, what will happen, and how we go down. For the first, for example, for the box, which is probably the most interesting and most surprising, given the fact that it gives exactly the other type of rotation what the beam element by default would do. Our beam element by default does this. So if just we accept the analogy as for the two bending moments, then we would always believe that independent of the information about how the connection looks like, the rotation is always like this. Now, in case of the most commonly used solution, is just the opposite. And why? Actually, this can be very easily understood if you just see that this flange, it comes into the zone with a certain rotation. That rotation continues into this plate. That plate moves to the right. It continues, it's a cantilever. Connected to this cantilever, they are moving together. Obviously, when they go out, the other must go to inside, and this deformation already happens. This other is already more difficult to explain so easily, but this is a very rigid connection here. So this here we have, and here what is also very important, that this can only happen with serious deformation of the web. So clearly here in this zone, the beam element is completely crazy. It has zero validity. There is a very strong section deformation. It's not warping deformation, but really a very strong web deformation. So if I was able to describe this with a beam element, then I would need to employ such a beam element which is really able to describe web deformation. The 7-degree freedom element cannot do such. So here the sequence is a bit more similar to a beam behavior because I stopped the serious deformation of a section by placing here in this turning cross-section a strong stiffener, and that's the reason that this deformation is more similar to what the beam element by itself would try to do without any information about the fact. And this is extremely important. Here the two effects are playing against each other, and finally they completely eliminate the warping deformation. If something comes into the beam, this is basically can be considered as a warping absorption device. So the two elements have opposite sides, opposite direction, and same size behavior, and the two finally kill each other, and there will be zero. So what we did in Consteel is that, of course, we are using beam elements, and it is possible in Consteel to make models with complex modelizations. It's possible to use beam elements, and for the corner use shell elements. We have constraints to consider the connect elements, including also the warping deformation. So everything is possible nicely to do, but it is slow and time-consuming to model a big structure like that. So we were looking for something maybe less precise, but quick and practically easy to be used solution. And then we found to that if we use this yellow representation, which was one of the others, and then we see how and which was the most critical one, there you see that the left is the shell, right is our beam. We defined here a certain constraint. We apply some automatic hinges. We don't let the beam element to transfer the deformation because it cannot. We are releasing it from this exercise, and we are enforcing a certain prescribed behavior to the connected elements because we know that in case of such a box configuration, what will happen? The beam element doesn't know. We believe that we know more, and when the engineer selects this topology, basically it gives an additional information to the beam element-based model, but is not stored and not included in the beam element, about the way how the deformation should be transferred. And we solve this transfer not by the beam elements themselves, but by additional constraint transmitting the deformations the way we want. Okay, and you see that it works absolutely nicely. When you select this option, then the rotation will be like. If you go, okay, and if we see if you look to the diagonal, so this was the box, and if you see to the diagonal, then actually it's not very well visible. Then also we do the same here, so we just reverse the deformations, and then we let the structure work in the direction we want. And in case of the box diagonal, it's visible that there is of course some deformation, but very small. And also in our solution, basically there is no any deformation. So if we go back to our original frame, when we define this corner, then we selected the very first one. This is that sort of corner. When you select this corner, then only the limitation of the cross-section designed as beam elements is applied. So we still not give any information about how the connection topology is made. The beam element transmits the warping deformation as it would do by analogy. And as we saw, in case of a box, this is completely wrong. In case of the diagonal, this is more or less fine. And in case of the combined box and diagonal, it's again completely wrong. Okay? If we know what is the connection, because we are the engineers, so hopefully we know how we want to design our structure, then we can help Consteel to have a bit more knowledge about the connection, and we can select any of the three, the category which is the closest. Okay, so for example, if you have a box type of configuration, then we can change this, click on apply, and then the color changes from gray to yellow. And if the column changes from green to yellow, then we implemented this additional information into the model to transfer this warping deformation in the corner. Don't forget, we don't have out-of-plane loads. So all the internal forces are in plane, no any warping, nothing. But there is warping in the buckling modes, which we will use to calculate the slenderness. So even that must be correct. Not only the internal forces, what we are designing for. These buckling shapes are exactly as important as the bending moment diagrams. And from the buckling shape point of view, this is a 3D problem, and this is full of torsion. Buckling mode is always the weakest part of the sections. That's what very many engineers say, that, oh, I don't need this complicated software, I'm designing always in 2D. Yes, but do they need to perform a TB check? Probably, yes.
Resistance is controlled by the outer plane.
Yeah. Okay, so now when I do nothing more, then I just run the calculation, And now this will be considered, this addition. I still have this message which I explained to you what it means. And now again I select all the other combinations together. I select the automatic, which is already the effect of the buckling sensitivity calculation, and run the calculation again. And the results did not change at all up to now, because again, on the column at least, because it's still the web local buckling is the relevant. So all the things what we do are having an impact on the slenderness. We have improved the slenderness calculation, which improves the LTV strength calculation. But as long as the local buckling remains the controlling, actually it makes no sense what we do.
Flange local buckling, hint, hint, hint. What do you do about it?
Okay. Now there is one other thing, and then we are at the end of this part of the demonstration, and then we can start to explain what will be the exercise. Is that actually when we define these column sections as 130 millimeter, Consteel at the moment works in a bit unprofessional way, at least from the perspective of a professional metal building engineer, because the maximum depth of the element is specified at the end, as it is visible also on the screen. But most of the engineers somehow believe that this height is not here, what they want, but this height is defined at the very last connection
basically at your end plate or at your connection plate there in the panel zone, yeah.
But actually Consteel doesn't know that, or at least is not able to put yet those two independent information together. So when I said tapering, the end cross section is here. Here is the 1030 millimeter defined, and linearly the section gets lower and lower and lower. By the moment we arrive the boundary of the column, the depth is already less. Although in the original design, the 130 was understood here. So because of this, in the original model, where Professor White said that he expects overstress in the rafter only, he artificially increased the beam depth the way that they will exactly reach the reduced expected size at the boundary of the column. So that's why
it's another geometry calculation, but you can figure out what depth you need where the column and the beam intersect to get 1,000 depth.
This is normally for a normal engineer, they don't care.
Right.
But
we're not normal.
But if somebody works for a metal building company, or at least wants to somehow prove that this software is good enough, then this is again a good chance to finally be disqualified, saying that you cannot get the good result. So
you can fix it.
We will fix it as software developers, but even in the meantime, you can fix it the way how Professor White did. And now I'm just trying to find what was his frame, and then we can quickly introduce his final depths, and then we are ready. I will find, I think that was an earlier file. So we will need to just adjust the tapering parameters for the elements which are coming in. Actually, that's also that we know that we have a very weak flange, but if we increase the height of the section, then we are still reducing the stresses in the anyway very weak flange, and maybe
very small flange.
Yeah. Probably the problem is even worse, but at the end of the day, you see now that these are the.
You've already got a very, very thin web at that panel zone, right?
Now here the column was already fine, but not the rafter, 130, and for. Actually, I don't know what was the. No, that's not the good value. Sorry, I don't know what was your good value. We should probably take from your original, if you can find it. Here on the column, it seems that we already used one, at least in this model, although this was not the value I told you to use. I think we used also 1050, 1050, when 1050 when we built the model. This is already the model what I gave to all of you to start the today's exercise. That already had, I think for the column, this was more or less the final depth. But for the rafter, we still see the 1030, which is, I think, is not it cannot be the final value. It's just too nice to be but actually we can leave it as it is because it doesn't matter.
Right.
We can say that this is the starting frame, okay?
Right, yeah,
So I hope you can trust that we had a version somewhere 2 weeks ago.
Yeah, even once we change
even yesterday actually.
Even once we change it, it still doesn't work.
Yeah, yeah.
So we need to do a modification to make it work.
Yeah, so anyway, so the idea is that we have small overstresses. And now here are the constraint elements. You see, here now they are visible. So this is the moment where we are adding an additional constraint bar into the stiffness matrix of the system, which will be the leading information regarding vorpictors. We don't let the beam elements to do the job because they cannot. And we inject additional information about the compatible deformations. Yeah, it's very interesting. And I'm pretty sure that no one is aware of that. So it's not only more extra welding cost, but it has also a beneficial effect. It has a yeah, but just people still consider a hinge there. Okay, obviously, even if we have a continuous connection between column to web, it's not a fixed end from LTB point of view because that's the poor column by torsion who would need to provide the fixity, and its torsion resistance is close to zero, but it's not zero, and that's a huge difference if something is really zero or just small. And many, many small things together are producing a visible something.